Good evening, ladies and gentlemen. So, we are Nachiappan, Palaniappan and Mohan Manivannan from LatentView Analytics, Chennai, and we are here to explain our methodology on how we rank the research institutions which contributed much to any conference that is of interest. So, this is our methodology. Introduction. So, ratings and reviews in today's world have a huge say in our decision making process or shortlisting process, be it the phone orders or to the institution selection, shortlisting. So, we always go by ratings and reviews and this thing. So, the one problem that we actually got to know after entering this competition is all the or most of the existing ranking methodologies use either non-transparent or not openly available, not accessible to everyone. So, the data is not available to everyone. So, as quoted in the reference paper by Anthony F. Van in 2005. So, the primary object of this competition is to rank the institution based on the publicly available data sets. So, we used Microsoft Academic Graph data. So, that is so all the features that we have extracted. So, we have extracted around 5 types of features. The first one is the reach, which measures the influence level, and the second one is a probability of each author, and the third and fourth are the joint probabilities, and fifth is the pseudo affiliation score that combines the joint probabilities. So, all these features that we have extracted are at the author level, and then we aggregated it to the affiliation or institution level. So, it is a bottom up approach. So, let me quickly walk into the first feature, reach. So, reach, we have come up with the algorithm to determine the influence level of each and every author given the author collaboration network. So, for each distinct field we have computed the author collaboration network, and then the reach of a particular author is computed based on the 2 level neighborhoods, 2 hops from each author. So, our primary concept behind this is, if an author is said to be influencer in this particular network, then he has to be surrounded by other influential nodes. So, only then we can call him an influencer. So, and the chances of him collaborating with another author is most likely if they are more related and if they have collaborated in the past. So, how much? So, the edge weight represents how many times the particular authors have collaborated in the past. So, as you can see from the formula, so the immediate neighbors are the weights of immediate nodes, immediate authors are summed up directly, and then the nodes which are at one distant or 1 hop away, so or 2 hops. So, there is a half likely chance. So, this 0.5 is based on our assumption, like half likely chance that this particular author can collaborate with the neighbor of my neighbors. So, that is the assumption that we have, and M1 and M2 are the number of, M1 represents the number of neighbors at to a node V or node of interest. Here it is Vi, and the M2 represents the number of second level neighbors to the node Vi, and here is a reach. The sample so reach of V1 is computed by 25 plus 15 and 0.5 of so neighbors of V3 and V2. So, and the next feature that we have extracted is probability of an author publishing a paper in this particular conference. So, this is based on our intuitions or assumption, like how an author is exposed to this particular conference. Okay. So, if you have already published a paper, so we wanted to measure that. So, so from the data and from 2011 until 2015, so out of these areas, out of these years, how many years he has published a paper, so we have computed. So, for 2015 we have 4 years and before 2011 to 2014. So, out of those 4 years, how many years he has published a paper, and you can see he has published two times out of 4, and So here if we have to, so this is the actual data 10101. So if we compute a ground truth out of it, like if we compare the predicted as well as the actual one having 0.5 as a cutoff, threshold cutoff, and we'll get 11101, whereas it is 10101. So it is close to 80%. So that is our basic assumption behind selecting this model. And then we have computed two joint probability scores, which I would like Mohan to explain about it.
Thank you, Nachiappan. So joint probability scores. This is how we calculate it. The first thing is like we try to look at 2 consecutive years of publication status for an author and just come up with 2 scenarios. The first scenario is the author published paper in the recent past T and published a paper in the year T+1 as well. So this is one scenario and we call it as joint probability 1. And next scenario is the author did not publish a paper in the recent past T but published a paper in the year T+1, which is the joint probability 2. So the idea behind this is like based on your past, we are trying to predict the future, but as a joint probability instead of just looking at as a probability. So this has resulted in more information than the probability score which we have calculated, which will be reflected in the model in the following. So I'll just move on to the how we calculate it, and for a particular author I will show you how we have calculated the value. So this is the joint probability 1 definition. The joint probability for publishing a paper in year T and in year T+1 is computed by taking the ratio of the frequency of the paper published in consecutive years to the sum of the frequencies of publishing paper in the year T and T+1 plus publishing a paper in T but not in T+1. So this is computed. I think I can explain from the example here. So here we have taken the author 5, hypothetical author 5. So for the year 2015, we'll calculate the joint probability score 1. So here you can see that he has a total sample space of 2. So the first sample space is coming from here. So in the 2011 he has published a paper, but in 2012 he has not published a paper. So this is one event. And another event is 2013 he has published a paper, and 2014 also he has published a paper. So that is the event 2. So that is a total sample space, and out of which the condition where the both conditions are true is where 2013 and 14 in the 2 consecutive years we have published a paper. So that is the reason we have 1/2, that is 0.5. And next we move on to the joint probability 2. So here the same goes here. So here the total sample space is just 1, and out of which he has published in the condition also met is also 1. So that is the reason we have probability 1. Next we move on to the pseudo publication score. So the pseudo publication score is nothing but it is trying to resemble the actual publication score which we are trying to compute. So here since we have the joint probability scores as well as the probability scores, we have the flow chart depicts what we are trying to do. We look at the past year whether he has published a paper or not. So for example here we take the publication status. We are trying to find out the probability, the pseudo publication score for 2015. So here we take the 2014 publication status. Here you can see that author 1 has not published a paper. So here in the joint probability 1 and 2 we take the joint probability 2 because he has not published a paper in the year 2014, and since it is 1/1 we have a threshold 0.5. If it is greater than 0.5 we allocate, we code it as 1. So we predict that he will publish a paper, and the average collaboration which we take it from the reach algorithm where we have a collaboration network. From there we take the average collaboration and we take the ratio of it, which is nothing but 0.5. And if you go to the author 5, the others are 0, so we'll go to the author 5 where in the 2014 he has published a paper. So we'll use the joint probability 1 which is 1/2.5, and we code the pseudo publication status as 1, and since the average average number of collaboration is 3, the score is 0.33, and this is the hypothetical the computed score, And this is from the original ground truth, where we have the status as A10101. So based on the true average number of collaboration, if you compute the author affiliation score, it's 0.5, 0.2 and 0.33. So in the last table we can see the similarity between the computed score and the actual score, where we are trying to get maximum similarity. Okay, so next we move on to the modeling part, where I think many people have described how they have prepared the training data set and test data set. We have done the similar thing, where we try to take the prepare the data till 2014 and predict it for 2015, and then use the model to predict it for 2016. So that is what we have done, and these are the heat maps which will show you the tuning parameter. We have used random forest model, and these are the tuning parameters m-try and n-try, which we can tune it and to get the best optimum value. So this is for the MM conference, KDD and the SIGIR conference, and in the bottom we have listed out what are the optimum values we have achieved. And for the NDGC for the MM conference, we have achieved an NDGC score of 78%, using an m-try of 7 and n-try of 900. And for the KDD conference, we have achieved a NDGC score of 79% at points m-try 5 and n-try 700, 200. The color coding tells us that it's more or less similar. And for the SIGIR conference, we have got 76% at points m-try 4 and n-try 200. And we have tried out different models like neural network, linear regression, support vector machine, and out of which random forest model has performed well for us. Next we move on to the conclusion. So the random forest model has performed well for us, and we have measured the variable importance using the optimum value, and the pseudo affiliation score, the joint probability score and the probability score have topped in all the three conferences. And if you see the number of people who have presented in the past, many teams have performed well in the phase 1 and phase 2, but they have failed to maintain that level in the phase 3. But if you see our model, we were able to perform consistently well across all the three conferences. The main reason we believe is because of the joint probability scores which we have derived, because that takes into account all the inconsistency in the last phase. You see there were many people who have published the paper only in the recent times, they were not consistent. That was the reason the pattern could not be identified using other models. But since we have used a joint probability score, even if they have not published paper in the past, and what is the likelihood they will publish the paper in the next year. So that was one of the reasons we think we could achieve a NDGC score of 76% even in the last phase. And directions for future research, location of the conference, information from competing conference and journals, direction of research trends in the related fields, and number of PhD theses guided by an author. So this is by intuition we thought will be useful for improving our model. So that's it.
Thank you.
Yeah, just